So today's lecture we will have discussion on X-ray absorption and detection of X-rays. So in previous lecture we had started with X-ray absorption and we had seen that when X-ray is passing through a material, X-ray will interact with matter and X-ray will be absorbed. So that absorption was governed by the expression I is equal to I0 e to the power minus mu by rho x rho, where mu by rho is called the mass absorption coefficient, which is a constant independent of the physical state of the system. So when X-ray is passing through a composition, maybe having different elements, in such situation we have to think about the weighted average of mass absorption coefficient, that is we have mu by rho, we have to take mu by rho as W1 into mu by rho 1 plus W2 into mu by rho 2 etc., where this W1, W2 etc. represent the weight fractions of the different elements or that component in the composite. So this mu by rho, importance of this mu by rho or mass absorption coefficient is that it varies with wavelength. When X-ray of different wavelength is passing through material, the absorption will be different. So this has got some significance which we were trying to understand in the previous lecture. And when we study that this mu by rho versus wavelength graph, when we plotted, it was found that as the energy of X-ray increase, so this graph I have plotted red one, which is that X-ray spectra, and another graph is also plotted on the same graph that is the variation of mu by rho versus wavelength. So in that case this black graph, that is as the wavelength decrease, that is as the energy of X-ray increase at some point, that is lambda k I have marked here, at that point suddenly this absorption increase, and this variation in absorption that is useful in different cases. For example, one, we can identify suitable filters. When X-ray is coming out from X-ray tube, we will be having characteristic X-ray spectra which is superimposed on a continuous spectrum. So we will be having K beta, K alpha etc. But for X-ray diffraction studies we prefer to have just a single monochromatic wavelength. So other unwanted this wavelength are to be filtered off. So in order to find a suitable filter for X-ray coming from a particular metal target, say from a particular X-ray tube, so we have to identify which is a suitable filter. For identifying suitable filter, this graph plays an important role. So in order to suppress this K beta radiation, this left side is K beta and this is K alpha. So in order to suppress this K beta, so we should find a suitable metal foil through which, or filter foil, that is through which this X-ray should pass through. And the peculiarity of that particular foil is that its absorption edge, for example lambda k, for that material will be in between, or the wavelength corresponding to this absorption edge should be in between K beta wavelength and K alpha wavelength of the target. So for example, when we use copper as the target, then we have got the wavelength K alpha, we have particular wavelength, K beta particular wavelength. So in order to filter out K beta, we should use a suitable metal. Generally the metal foil used is nickel. Nickel is having Z atomic number. For example, copper, atomic number of copper is 29 and atomic number of nickel is 28. So generally when we use filter, the atomic number of the filter material should be nearly 1 or 2 below the atomic number of the target. So this information we are getting from this graph. So while analyzing through some method, so we will be able to understand which is a suitable filter foil. For getting that correct filter foil, we have to go through this Moseley's law. So in Moseley's law, we have seen that this frequency, square root of frequency is directly proportional to the atomic number. So square root of frequency of the characteristic line. So here nu is equal to C into Z minus sigma, where Z is atomic number and C and sigma were constants. So this Moseley's law, if we carefully analyze, it comes from that Bohr atom model. In Bohr atom model we have energy of nth orbit is given by E is equal to minus mz square e raised to 4 by 8 epsilon 0 square n square h square. So, where m is the mass of electron, z is atomic number, E is electronic charge 1.602 into 10 raised to minus 19 coulomb, epsilon 0 is absolute permittivity, n is the orbit number and h is Planck's constant. So, in this case this is the, suppose if it is k orbit, then this will be n1 and this will be energy of the first orbit. If it is L orbit, then we will be having E2 and correspondingly we will be getting N2. So, when we are studying the energy of k alpha, the electron from L orbit is falling into k orbit. So, the difference between the two energies will come out as k alpha radiation and its frequency is directly proportional to atomic number. This is what Moseley's law. So, therefore, if we take this expression, then when you calculate delta E, the change in energy when an electron falling from L orbit to k orbit or m orbit to k orbit, the corresponding energy difference when you work out, you will be getting some physical data here, something that is except this 1 by n square, except 1 by n square. So, everything will be there and only 1 by n square will go to the other side and minus m z square e raised to 4 by 8 epsilon 0 square h square into this 1 by n1 square minus 1 by n2 square or 1 by n2 square minus 1 by n1 square. That is a term you are getting. And this term, so this delta E is the change in energy that is given by h nu. That h nu is given by this two brackets. That means there comes z square. So, delta nu h nu is proportional to z square or nu is proportional to z square, or therefore nu is equal to square root of nu is proportional to z. This is how we are getting that expression. So, that means when we analyze this graph, if the energy of X-ray increase, when it comes to a particular point, particular energy or particular wavelength, suddenly this X-ray is absorbed. That is in our X-ray tube, when we are discussing, we found that X-ray production, a high speed electron which is having sufficient kinetic energy, when interact with electron in the k orbit, that electron will be knocked out. So, the energy of the electron, energy of the moving electron should be sufficiently high enough, so that should be able to pull out electron from the k shell. So, that is what we are talking is the energy which is required is that E into V, because of the external potential difference which is applied. So, similarly, whether it is electron or whether it is X-ray, if the energy of that photon which is interacting with this k orbit is having sufficient energy, then similar to that electron which was knocking out electron from the orbit, this X-ray photon will also be able to knock out electron from the orbit. But there is a difference in name here. When electron interact with the target and k electron is knocked out, then corresponding X-ray which is coming out is called characteristic X-ray. Whereas in the case of X-ray, if X-ray photons are interacting and if k electrons gain that energy and it goes out, then atom will go to excited state. Because of that, there is a vacancy in the k shell and electron from L shell will come down to k shell and that is a photon will be released. So, in this case that X-ray photon which is coming out from the atom is not, we will not call it characteristic line, but we will call it X-ray fluorescence. And the electron which was knocked out, which will be gaining kinetic energy and it will be coming out, and that electron is called X-ray photoelectron. So, this X-ray photoelectron which is coming, that gives an information about the material, and this X-ray fluorescence which is coming out, that also will give information about the material. So, these two are also used by the material scientists in order to understand the nature of a particular material, and they call it X-ray fluorescence spectroscopy, XFS, or X-ray photoelectron spectroscopy, or XPS. So, this X-ray fluorescence spectroscopy or X-ray photoelectron spectroscopy could also be used in order to understand the oxidation state of the system or to understand the purity of the material. So, many cases these XPS and XFS are also used. So, here, so when X-ray is coming, our X-ray energy is increased, at this point X-ray is absorbed, and because of this absorption, that K electron will be knocked out, and correspondingly you will be getting XFS or X-ray photoelectron and X-ray fluorescence. So this particular wavelength, this idea can be used in order to understand the energy of different or energy levels inside around the nucleus. There are energy levels, K orbit, L orbit, like that. So we will be able to figure out and we will be able to calculate the energy of these various levels by analyzing this graph. For example, when X-ray energy is increasing, initially there is not much absorption, but at this point the X-ray photon is completely absorbed, means that energy of the X-ray, because here lambda k is the absorption edge, therefore that lambda k represents a particular energy. That energy is given by E is equal to hc by lambda k. This is the energy of X-ray photon. When energy of X-ray photon is increased to this particular value, this target material or that material is happy to absorb it, because this energy is equal to the energy of that K electron, or that K electron can be knocked out by absorbing this energy and electron will be out. Therefore, this gives an information about the energy of K orbit. So what we call it W, we can call it the Wk, which is the energy of K orbit. So similarly we can find out the energy corresponds to WL, energy of L1, or energy of L2, energy of L3. So like that we will be able to calculate exactly what is the energy of first orbit, energy of second orbit, energy of third orbit, etc. by analyzing this graph. This graph may be further extended. So you may be having more discontinuities like this. You will be having more discontinuities, and these discontinuities correspond to the absorption edge for K, absorption edge for maybe lambda corresponds to L, maybe corresponds to M, etc. But as we go towards right side, then energy gradually decrease. Sometimes it may be possible even with ultraviolet light. But if ultraviolet light is used, and then ultraviolet light energy may be sufficient to pull out electron from L or M shell, may not be possible with K, will not be possible with this K. So if electron from L shell is removed, the possibility is only M orbit electron can fall into that, and you may be getting L alpha. If electron from M orbit is released, there should be an N orbit, then only electron from N orbit can fall into M orbit and you may be getting M alpha. So the probability is decreasing. Therefore, generally we come across only K alpha, K beta, and our interest is to suppress K beta so that K alpha, the intense high energy K alpha, can be pulled out, and that can be used for X-ray diffraction. So while analyzing, so using this idea, you will be able to supply here and you can find out what is the energy. Suppose you want to identify a suitable filter, then for that filter what is the energy of K. So by studying X-ray absorption behavior of that material, you may be able to calculate what is energy corresponds to Wk, what is energy corresponds to WL, what is energy corresponds to Wm, etc. You can be plotted. Suppose we consider a neutral atom. So neutral atom, whatever is the energy, that energy we assume it as 0. So this is neutral atom. Neutral atom, and when we come towards that left side, there comes lambda k. That lambda k corresponds to the energy of X-ray photon which got absorbed and the K electron is removed. So that energy of X-ray photon, that is the energy corresponds to K level. So that K level can be marked somewhere here. So this is Wk, which is highest, whereas lambda L was little right side. So correspondingly you can find out what is the X-ray energy or X-ray photon energy when it was absorbed and correspondingly L electron was knocked out. Then that energy will be WL. That energy will be WL. Similarly you can plot WM, etc. So this is approximate, that is we will be able to plot the energy level diagram of a particular system by studying the absorption coefficient versus wavelength. So in this case, initially atom is neutral. When X-ray is absorbed and suppose you have reached up to lambda k, immediately atom will absorb that energy and it will go to Wk. In the sense, initially atom was neutral, now Wk energy of the X-ray photon is absorbed by the atom, so that atom is having a higher energy, and we say that there is a vacancy in k orbit. So atom absorbed and the energy of atom is increased. So this axis indicates energy of the atom increase. Now when an atom is in this energy level, it is not happy because it is in an unstable state. So it prefers to go down. So what we say is, we speak in a different language now. That is the first way we spoke, that is electron from L shell will be falling into K shell. So we say that energy will be dropping from Wk to Wl. So this will be going down and we will be saying that energy drops down. If electron is jumping from M orbit to K orbit, we say that energy drops from Wk to this one, M. So this corresponds to K alpha, this corresponds to K beta. So we will be getting K alpha, K beta, and K alpha energy, this is energy difference which is K alpha. This is energy difference between which gives K beta. So K beta is having higher energy, so it is in the left side on that graph. So this is how we are explaining. So by studying this mass absorption coefficient versus wavelength, we may be able to plot energy level diagram for a system. So from this energy level diagram, suppose you want to find a suitable filter. If we know the energy level diagram which is plotted with the help of that lambda k absorption edge, if you are plotting like this, then you know that what is the energy of K level, what is the energy of L level, etc. for that particular new material which you are planning to use as filter foil. So from that you will be able to figure out what would be the value of Ek, that is energy of K, what will be the value of energy corresponds to El, Em, etc. for that new material. As well, you can also find out what would be the difference between these two, correspondingly what will be the K alpha value for that new material. So like that, different information you can collect from that. So from that, if you know the Wk value of that filter material, then you will understand that that particular X-ray photon, if X-ray photon having energy that particular Hc by lambda k, if it falls, then it will be fully absorbed. So you are going to filter out. So you are that is from this diagram graph, you will be able to figure out what will be the exact wavelength lambda at which you are getting lambda k. So if you are selecting suitable materials such that the lambda k of the new material is in between the wavelength corresponds to K alpha and K beta of the target material in the tube, then you will be able to plot the previous graph. That is the graph that absorption edge will be in between K alpha and K beta, so that K beta will be suppressed and K alpha will be comfortably safe. So that means you will be getting an intense K alpha out, and that intense alpha can be, or K alpha can be used for X-ray diffraction studies. So where you will be using these information, that is you are finding what is the frequency, what is the wavelength, or how this atomic number is a parameter. So here atomic number, generally if for X-ray diffraction studies, the target materials, their atomic number may be in the range from 20 to 29 or 30 or 30 like that. So for these materials you will be able to calculate Wk, Wl, Wm, etc. from their absorption characteristics. From that you will be able to tell what is the value of that lambda k. You will be able to speak about what is the value of expected that frequency of the K alpha if that material is used as target. So many such information you will get from that. If you work out, it has been found that in many of the filter materials, the atomic number of the filter material should be either 1 unit or 2 units less than the atomic number of the target used, so that the absorption edge lambda k will be exactly in between that K alpha value and the K beta value, and you will be able to suppress K beta to a greater extent. That is one. So that is a major advantage of using that absorption spectra, or that absorption versus wavelength graph. Now the requirement is we have to go for detection. When we go for detection, the X-ray which is coming from the tube which will be falling on a material, and it will be getting diffracted, and this diffracted information X-ray will be collected, and it will be detected. From that we will get information about the material. So for that, this X-ray intensity should be sufficiently high enough. If the X-ray intensity is sufficiently high enough, then only we will be getting sufficient information from the material. So for that, this X-ray, in order to increase the intensity of X-ray, so we have to, inside the tube we have to send, or we have to increase the input power. That means input current flowing through the tungsten filament should be increased, correspondingly more electrons should be released, and these more electrons should strike, that is within short time many electrons will be hitting. So in that case, we have seen that such a high energy electron, when it is hitting the target material, then this kinetic energy of the electron is getting converted into X-ray and heat. Less than 1%, maybe less than 0.5%, that much only converted into X-ray, and more than 99% of the kinetic energy of the electron is converted into heat. Therefore, if we increase the that input power or input current, then correspondingly more number of electrons will be hitting in the shortest time. Therefore, if it is hitting at the same point on the target, then the heat so produced will be enormously high, and that may damage the target. Then we will be compelled to reduce the X-ray intensity, or compelled to reduce the input power. If we reduce the input power, then we will be getting less intense X-ray, and less intense X-ray cannot give appreciable information when it is used for X-ray diffraction. Therefore, in order to increase the X-ray intensity which is coming from the target, the possibility is, instead of using a stationary target, we will use a rotating target. So if the target is given a rotation, throughout the time we will be getting new new regions of target will be facing this incoming electron, so that the electron will be hitting always on new area, so that this heat production can be controlled. Correspondingly, the input power can be considerably increased, so that you will be getting high intense X-ray from the tube, and that high intense X-ray can give comparatively better information when we are using it for X-ray diffraction. So this high intense X-ray, when it is used and when it is diffracted, it will be coming out, and that should be collected and that should be analyzed. That is our X-ray, or that information about the nature of the crystalline structure. So for that we should have proper detectors. So mainly three types of detectors are used. First one is X-ray fluorescence method, or X-ray fluorescence screen is used. Another method is X-ray photography, that is photographic plate will be used, and the third one is X-ray counters, or maybe ionization chamber. So in X-ray fluorescence, basically fluorescence means it is conversion of invisible radiation into visible radiation. That is fluorescence process. So in X-ray fluorescence, the X-ray which is coming from the material after diffraction will be allowed to fall on a film or a screen which is having fluorescent coating. Some cardboard backing with some fluorescent coating like zinc sulfide with some amount of nickel will be used. So when it is falling on that, it will give the information, or that fluorescence will be produced. Fluorescence means it will fluoresce. That is, this X-ray, when it interact with this fluorescent material, it will be converted into visible light, maybe yellowish color or something. So that visible light is an information that X-ray is coming. So generally fluorescence is used for the detection of X-rays. It is a little difficult to get exact intensity of the X-ray which is coming from this material. Therefore, this fluorescent, many a situation, along with this fluorescent material or fluorescent screen, sometimes a photo tube will also be attached. In that case, the combined system, we call it a scintillation counter, that will give a better information about the intensity of X-ray which is coming out. Second method is photographic plate. So in photographic plate, in a visible light also, if visible light is allowed to fall on photographic plate, it will be exposed. If it is exposed, then we will get information on the photographic plate. But visible light, the energy of the visible light is comparatively less. So same photographic plate cannot be used for X-ray, because X-ray is having comparatively high energy, it is very high energy radiation. Therefore, in order to collect X-ray information, the photographic plate should have a reasonably thick photographic emulsion. So therefore, generally a transparent sheet with a photographic emulsion will be given on either side. So the thickness of the photographic that is coating should be high. So when this thickness increase, naturally the grain size also will be increased. So in order to get a very precise fine information, we have to enlarge the data But when we enlarge this, if the grain size increase, then we will not be able to take the perfect information from that film. Therefore, in the case of X-ray, since already the grain size is big, so when you enlarge it, so naturally the fine information may not be available from the photographic. This is a difficulty with X-ray photographic film. Another difficulty with X-ray photographic film is that we call it sensitivity or film sensitivity. That is, imagine you are allowing same intense X-ray with different wavelength. Same intensity but different wavelength X-ray are allowed to fall on same film or similar films. In that case, the blackening probability, when X-ray is falling on, the film will be blackened, and the blackening probability, that is your information. That probability will be again different because of the difference in wavelength. This is what we call it film sensitivity. So, particularly when we collect X-ray, and if there is a continuous range of wavelength, then even if the intensity is same, this will be giving different type of that is interaction. So, that is again a problem generally sometimes we come across. So, these problems are not seen in the case of that counters or ionization chamber. In ionization chamber, X-ray can ionize gas. If it is allowed to pass through a gas, then gas will be ionized, then it will be converted into positive and negative ions. So, imagine we have got a X-ray ionization chamber, a tube within which some suitable gas is taken, and there are two electrodes which are connected outside to a meter or something like that, a current detecting device. So, when X-ray is passing through this gas atoms will be ionized, and you will be getting positive ion and negative electrons, and these positive ion and negative electron are attracted towards the electrodes, and when it comes in contact with the electrode, immediately a current will be noticed, current or a surge current will be indicated at the output. That is an information. So, that is how we will be able to detect X-ray, that is when it is coming from X-ray or from the material from where it got diffracted. So, sometimes this current again, if the intensity of X-ray is constant, if the intensity of X-ray falling is constant, then this current also will be constant. If intensity of X-ray is varying, that is the amount of X-ray coming from the diffracting material, if it is having a continuous variation in intensity, correspondingly there will be continuous variation current, and that is an information about the nature of the material. So, that is how we are using ionization, and sometimes this current may be again fluctuating depending on the intensity of the fluctuating, then correspondingly we will be getting a fluctuating information. So, that is the image, or that is the correct picture of the material. So, this is how we discuss about X-ray detection. So, in the previous lectures we had seen first one we had seen what is X-ray, then the following we had seen what is the nature of X-ray, then after which we came across X-ray production of X-rays, then we came across these X-ray spectra, X-ray characteristic spectra and continuous spectra, then we came across the detection or the absorption of X-ray by matter, then how X-ray filters can be used, and the last one, how X-ray can be detected. So, this forms the preliminary basic information for X-ray diffraction, which in order to further proceed with X-ray diffraction, we should have a reasonable better understanding on the crystal nature and crystal structure, etc. Those things will be discussed in the following lecture. Thank you.